ideal systems, the equilibrium is given by yi of t and p. Well, it's given by yi equals ki of t and p times xi. I equals 1, 2, and 3. So for an ideal system, I have something like this. I need data. You've got it. Looks like this. Let me plot t along here. Let me plot all my k's up this way. And let me suppose they look something like this. Well, they don't really look like that. Let me suppose they look something like that. Oh, something like that. Something like that. So this would be K for butane. This would be K for pentane. This would be K for hexane. This diagram has been drawn at some P. In particular, it'll be drawn at the P you're interested in. Now, somewhere here, I have the value K equal to 1. K equal to 1. So I'll draw a line across there, and I'll notice that at this T right here, which I'll call T down star, and at this T right here, which I'll call T up star, the following interesting thing is true. For T's to the right of T up star, for T greater than T up star, all K's are greater than 1. For T less than T down star, all K's are less than 1. So it's only between T down star and T up star that I can have K's on both sides of 1. And I'm badly going to need K on both sides of 1. Yeah?
What is K? Is K like a number?
It's defined like this. That's what it's called, a K. We talked about this the other day. Ratios of K's were alphas. Alphas are called relative volatilities. So the K for the more volatile component is higher than the K for the intermediate volatility, is higher than the K for the lower volatility. And this is equilibrium information, so you need to be given it. This is equilibrium stuff. So you need to be given it. Notice that F equals C minus P plus 2. P is 2, so F is C. Now, my number of variables is equal to 2 times C minus 1 plus 2, which is 2C. So I'm entitled to C equilibrium equations. C equilibrium equations, and these are them. This is true for I equal to 1, 2, 3, dot, 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 C. These are my C equilibrium equations. C equilibrium equations. Okay? Now, of course, you have to have data to make it work, but at a given P, I'm entitled to a curve like that. Somebody comes and says to you, oh, but the P is some other P. Do I have to have these curves at all possible P's? And you say, well, I don't think so, because Ki of T and P times P equals Ki of T and P0 times P0 for an ideal solution. So if I've got K's at P0, I can get K's at P. So once I have this data at some P, I can turn it into data at any P I want. All right? Now that's kind of important. So you picked up on that? Okay. First thing I might like to do is talk about the dew point and the bubble point of a solution. You guys ever heard of dew point and bubble point before? Yes. Yeah. Ah, you're through telling me no, huh? Good for you. Yeah, you've heard of it. People have told me they've taught you this. They've told me you didn't learn it, but that doesn't mean you ain't been taught it. So, let's talk about dew point and bubble point, but let's draw a picture about dew point and bubble point first. Dew point, bubble point. So, let's have a picture so we have a clear idea of what we're talking about. The easiest picture to draw is a picture at c equal to 2. It's a little bit harder to draw the picture at c equal to 3. We can make some stab at it, but at c equal to 2, we can be precise. C equal to 2. Now, if I'm going to talk about dew point and bubble point, I have to do several things. I have to set the pressure. So I'm talking about dew point temperature and bubble point temperature. So dew point and bubble point temperatures. Had I set the T, I would have been talking about dew point and bubble point pressures. Okay? But right now I'm setting the P, and I'm going to talk about dew point and bubble point T's, and for C equal to 2, I have this nice TX diagram. It looks something like this. This has been drawn at the P of interest. And here's how this goes. I set a composition. Set Z. All right, here it is. And I'm at the right P, and I'm at the right Z. And I begin, so I have a cold case. So here I have, X equal to Z, and I got P equal to 1 phase. So I've had to set a T, a P, and a composition. Makes my 1 phase well defined. So I warm it up. It's still liquid. Same X, which is Z, and the same P, higher T. Finally, I get it to this point right here. This temperature right here is called the bubble point temperature, which is a function of, which depends upon the P I set and the Z I set. If I set another Z and I start heating this thing up, I get up to here and the bubble point's there. So the bubble point depends upon the pressure you set and the composition you set. And I'm going to call the X's Z when they're liquid. And the first Y that comes off in a negligible amount has that composition. That's the composition of the bubbles that form. And then I keep heating this thing. Sooner or later I get to here. When I heat above here, I get to here. Now I'm in the vapor range, and I call this now Y equals Z. And I got a vapor phase, single vapor phase up there. And I turn around and I start cooling it, and I come down here, and the first drops of liquid that I get form and make liquid here, and I get what I call T dew point. So I inputted a Z, I input a P, I learn where the bubble point temperature is, I learn where the dew point temperature is. So I have two things going on here. A bubble point is a function of P and X, and a dew point as a function of P and Y. But of course, these X's and Y's were the Z I set originally. Okay? The only time you get X's and Y's that are not Z is when you move through this region. Then I get X's here and Y's here, X's here and Y's here, and so on. Clear? If it ain't clear, say something. Now I can redraw this if you could stand it, sort of. I can draw a three-dimensional curve and I can say somewhere in here there's, yeah, I really can't do this, I guess. Somewhere in here there's a surface. What do I imagine I'm talking about? I guess I'm going to plot T up this way. I guess I'm going to plot x1 or z1 and y and x2, well, x1 or y1 and x2 and y2. So if I pick a point in here, I've got a composition, an x1 and an x2. So here's a composition x1, x2. It's liquid, it's cold. I'm drawing this at a given P, and I've got some surface here that corresponds to this line, and I've got some other surface that corresponds to that line, and between them there's space. So there's a one-phase liquid region below that one surface, and there's a one-phase vapor region above that surface, and in between is a two-phase region. So I begin heating this guy. And when I get to here, when I see the first bubble, I say that's the bubble point temperature. Okay? Then I can go through the two-phase region, come out the other side, and I will have located the dew point temperature. And it's not the best diagram in the world, but that has all the information you want. So let's try and calculate a bubble point and a dew point. So how will this go? So here I am at the P of interest. So here I am. And I set a composition. Say Z. And I make it cold. So I've got a liquid. So if I'm cold, I have a liquid, and the composition of liquid X is equal to this Z I set. And what am I going to do? I'm going to increase the temperature until I get a bubble of vapor formed. And at that point, I'm going to say Yi equals Ki T and P times Xi. Now these Xi's are given, and this P is given. All right? So I'm going to sum this equation. 1 equals the summation Ki of T and P times Xi. I'm going to take the 1 to the other side, and so my equation will be this. Summation of Ki of T and P, P given, minus 1 Xi equal to 0. These Xi's were the original Zi's. This P is known. This is at one equation and one unknown. The unknown is T. Everything else is known. The T that I'm going to get out of here is called T bubble point. Okay? So I've got to solve this problem for T bubble point. So what do I do? Well, you know what I would do. I would draw a graph.
Professor, shouldn't the minus 1 be outside the parentheses?
No.
Or
Look. I don't have any problem with you putting it outside the parentheses. This is equally correct.
okay.
It's the same thing. But I want to write it like this because, well, because it's very convenient. So what am I going to do? I'm going to plot the summation of,
Dr. John,
yeah,
how's it the same thing since you're not multiplying by
where's the voice coming from? Ah, let's hear it.
So you said that you can take the -1 out of the parentheses of the summation?
Because summation of x's is 1.
Okay.
Okay? So, what am I going to do? I'm going to go to my diagram at the P of interest. Here it is. P is given. K's are being plotted versus T. And I got these things on here somehow. And I got the place where K is 1. And this is located T down star. This is located T up star. Okay, now take a look at my equation. I'm going to plot this thing. And the question is, can this ever be 0 if all k's are greater than 1? No opinion.
No.
Remember, the x's are all greater than 1. There's a parenthesis here that's kind of hard to see. So if all k's are greater than 1, then all k minus 1's are greater than 1. These are all positive. This can never be 0. So I never look for a solution beyond here. No way. All right? Next question you would ask is, can all k's be less than 1? No, because all these guys then are negative. These guys were all positive. The sum has to be negative, so you will never look for answers. No way. So my answer lies between T down star and T up star. So I do the following. I plot summation of whatever that stuff is versus T between T down star and T up star. And I find a curve that looks like that, and that is the answer. T bubble point. Depends upon the P, and it depends upon the X's. So I've got the bubble point, okay? So in general, I will make use of the fact that in systems like this, if I want to talk about a bubble point problem, I will always say, oh yeah, the bubble point equation looks like so. The bubble point equation is summation ki of t and p zi equals 0. So I'm always going to think about the bubble point equation like this. If I'm talking bubble point, the z's are x's. Now, we also want the dew point. So, what am I going to do for a dew point? Well, I'm going to take this z, heat this stuff all the way up, so I get one vapor phase, start cooling it, and write. So for dew point, I'm going to write, what am I going to write? yi, the y's are now z's, or the z's are now y's, over ki of t and p equals xi. Y's are known, p is known. I sum this, summation of 1 over ki of t and p minus 1 times the yi's is equal to 0. I'll probably write that slightly differently. I'll probably write it as